So we have discussed causality. Now anybody ready with shift invariance? You like to come? Yeah, sure. How would you describe?
Shift and the invariance is like we give a input and take the output and shift the output, that we consider it as a y1, and then shift the input and give it to the process and we'll get the output y2. So if y1 equal to y2, you can say shift and.
Would you like to write down formally? Very
Formally,
good.
okay.
Yeah.
So we have a, so I'll draw this one.
Sure.
We have a x of t, and then if we process.
Can you explain what you have done?
So this one is the input we are given to the process, we got output.
Yeah.
So I have shifted this output, so I got y1 of t, and see this is the input I have shifted, so I have written it as x1 of t. Then I go into the same process, it's y2 of t. For the differentiation, so if both are equal.
Very good. That's very correct. Yeah,
Same,
and
same.
the,
Yeah.
the shift is the same. The two qualifications, yeah, very correct. The two experiments, yes, that's correct. That's very correct, you know. So you have two experiments. In the first experiment, you give an input, observe the output, and of course, as he's described, you could shift the output and then give a shifted version of the input shifted by the same amount, and if the output the second time is what the original shifted output was, then the system is shifting, and this should happen. See, what is important is that this should happen for all such inputs and for all such shifts. That is important, you know, the occurrence for all inputs and all shifts, otherwise it's not valid. Okay. Now, you see, similar, it's very good. So now you're getting the idea how, you know, what is the system property, isn't it? Let's finally talk about stability. What do you mean by stability? Be, of course, bounded. Who would like to come? Yeah, please.
Sir, I am Srinivasan from MIT Manipur.
Very good, yes.
Bounded input, we will be getting the bounded output.
Yeah.
So this is a plant. There is a model there. So for a bounded input, so you get a bounded output. Then it is fine.
What is the experiment and what is the consequence?
No, if you have bounded input and then if your then system is linear. So here for a same bounded input, if I get a non-linear, that is unbounded output, then it is a non-linear system.
Non-linear or?
Sorry, unstable. Unstable.
I think that's correct. So, you know, we'll take that. So, that's very correct. Yeah, Srinivas has correctly said that stability requires that the experiment be performed, that is being performed is to give a bounded input to the system. And the consequences, the output should be bounded. That's what is required for stability, right? So, it's simple. Now, what is boundedness? Boundedness means that there is an upper limit on the magnitude of the input, right? The same. Of course, the upper limits can be different for the input and output. That's possible. Very good. So now we've seen some important properties. Now, similarly, there are other properties. You see, now some properties. Now, I'm leaving this as an exercise for you, right? There are some properties where you will find that those properties are included in others. For example, memory, you know, is related to causality in some way, right? They are not totally independent, right? Invertibility is also a property, right? It's a property agreed, but there, you know, it's a little more complicated. What do you mean by invertibility? When you say a system is invertible, right? And you have talked about symmetry and so on. Now, you know, symmetry, now, of course, you know, I would recommend that now I won't want to go into all the properties now, right? Think about the other properties, see which of them are really properties, and you must also see whether they are properties of the signal or properties of the system. So, you can think about the other properties, right? Now, similarly, when you are looking at properties, you must think, see, the most important properties, the fundamental properties are these 5 properties. What are they? Additivity, homogeneity, shift invariance, causality and stability, right? These are the 5 important system properties. All right. Now, the next idea that you need to discuss is, see, in fact, now we are going to look at a different question in the context of signals and systems. The question is, how do I characterize a system? How do I characterize a system? So, today we will look at the characterization of a system in the natural domain. Later on tomorrow, maybe towards the end of the day today and tomorrow as well, we look at the characterization in the alternate domain, the transform domain, right. So, so tomorrow we will start, in fact even today we will start with that discussion. What is meant by a transform domain? What is meant by going into a different domain? Why do we need to do that, right? Now, you see when a system has some of these properties, which properties? Linearity and shift invariance. And linearity is a union of two properties, additivity and homogeneity. And it also has the property of shift invariance. Now, before we go on, before we start discussing the mathematics of all this, let's also ask ourselves, why are we discussing these properties, right? What is it in the physical world that brings linearity, or what does linearity mean in the physical sense, and what does shift invariance mean in the physical sense? Now, instead of doing think, pair, share, I will ask you to volunteer. Any volunteers? Tell me what is, let us take shift invariance first. What is the physical meaning of shift invariance in a system? Yeah. Let's have you come forward, because
one example we can take of this LED light. So, LED light, if I turn it on, so same intensity of light it will give now. Yeah. If I turn it tomorrow, again it will give same intensity of light. Right. So, output of this LED is time invariant.
Time. Very good. That's right. See, what is the physical implication of shift invariance? The physical implication of shift invariance is essentially the fact that the system does not change its behavior in time. Now, in fact, you want that very often, right? Now, you are coming to class today and you have a nice air conditioned room, and you have properly lighted room and ventilated room, right? Now, when you come tomorrow and you turn the switches on, you don't want the switches to be inoperational. You want them to behave the same way as you did today, or you don't want the switches to start changing their function, right? So, shift invariance means when I behave, if I look at if I give the input now and I see a certain output, and if I give the same input a little later, the same output should appear later, right, displaced in time. So, that the system continuing to behave as it does is the physical meaning of shift invariance, right. What is the meaning? Yes. Practical. So, he gave a practical. He said, I came and switched. Yes. So, yeah. Oh, light will not. So, if it's raining, then if. It is not the light only which produces the same amount of intensity, but because of fog or something, we are unable to observe. So, there are two systems involved here. One system is the LED lighting, which no matter whether you turn it on today or turn it on tomorrow, unless there is something wrong with the supply, it is going to give the same kind of lighting. How that lighting is perceived by your optical system, by your body, will of course depend upon the ambient conditions. If it is very dark outside, then you will perceive the light in a certain way. So, the perception system of the human is another system which has been cascaded. It has been followed. It follows the lighting system of the LED lights. Is that right? So, there are two systems. Yes. So, when you are designing a system, you need to worry both about the system which you are trying to design and the system which would follow it or precede it. Sure. Yeah. Anyway, so all these ideas would come up when you teach in a classroom. Now, you see, the important thing is when a system is both linear and shift invariant, right, when it obeys. By the way, so additivity and homogeneity are easy to understand. right? And well, I mean, any of the electrical circuits is additive and it's homogeneous as well. And if it's also shift invariant, provided the element values don't change in time, which is mostly correct. But you know, if the element starts wearing out, then of course there's a problem, right? Now, if a system is both linear and shift invariant, we want to perform, see, now the next step is to characterize the system, right? So, what do you need to do when you want to characterize the system? Again, you want to perform an experiment on the system, look at the outcome, and then you should, what do you mean by characterization? I perform an experiment on the system, look at its outcome, and that should tell me about many more possible such situations. That's what characterization means, right? So, for example, I give this particular input, I observe the output, right? Having made this observation, now I want to be able to say what the system will do when I give it many different other inputs, right? So, for a linear shift invariant system, all of you must have heard the term impulse response, or many of you must have heard the term. How many of you have heard the term impulse response? Many of you have heard the term. This word is oft quoted, right? And often not understood quite well, right? We don't understand why we should be looking at the impulse response, what is the significance of the impulse response, or what the impulse response really is in the first place, right? Now, let us understand the impulse response very informal. You see, the impulse response very informally means the following. You think of the input as comprised of many small pieces, right? So, you take, suppose this is the input waveform in a system. You think of the input as broken up into many small pieces, in fact, in the limit, infinitesimally small pieces. And the idea of bringing in the impulse response is that I should be able to look at one particular input, which is now, you know, when you think of an impulse, think of it like this. You had an input which lasts for a very small time. You have an input which lasts for a very small time, right? And you look at the output. Now, if the system is linear and shift invariant, what are the two things that are going to happen? If I have many such pieces which are superposed, which are added to one another to get the full waveform, the resultant should also be the sum of the individual output. That is the first step. Secondly, if I scale each of these pieces by a constant, the output should be scaled by the same constant. Is that right? The third is when I shift any of these pieces by, so if I have looked at what happens when a particular piece is given, when the same piece is shifted, the output is also going to be shifted. So, linearity and shift invariance requires, or rather we can say, if I want to be able to characterize a system only with looking at one such small piece, it requires both linearity and shift invariance. Now, take a minute to appreciate this. You see, if any of these properties, now tell me, now here I want you to do again an exercise in discussion among yourself. I have told you the importance of, you know, I said that if I take a very small piece of a waveform like this and I study the output, it tells me everything about a linear shift invariant system. My question to you is, take each of these three properties, additivity, homogeneity and shift invariance, and tell me if each of these is violated, where is the problem? Why can't this characterize a system completely? So, again do a think, pair and share. This time we will take, you understand the question? So, when each of these properties is violated, right, that means when additivity is violated, where is the problem? When homogeneity is violated, where is the problem? When shift invariance is violated, where is the problem in characterizing the system? If I make only one experiment on it, the experiment is give a very small short lasting input like this study its output, and that should tell me everything about the system. Okay. Why is the impulse response meaningful only when the system is linear and shift invariant? Very often this is not properly understood by students, right? So now you take a couple of minutes. I think, here I would recommend, instead of doing think, pair, share every time, each of you can think, also discuss among yourself, and we can have volunteers. We don't have to do a formal think, pair, share. You can take a minute to discuss among yourself, but then let me have volunteers to answer for each of them, for additivity, for homogeneity, and for shift invariance. Yeah, now this we just have volunteers. Any volunteers? Yeah, very good. Which one would you like to talk about? Yeah.
First, let us deal with homogeneity.
Okay. So he's saying, suppose homogeneity is violent.
Yeah.
Where is the problem?
Yeah. So here you can see that this is my signal. So this signal is nothing but addition of different impulses.
Yes.
And this impulse has one amplitude, and if you take impulse over here, this has a different amplitude.
Very good. Yes.
So I cannot generalize if homogeneity is violated.
Very good. So that's very correct. If homogeneity is violated, then I can't say what will happen to different heights of impulse. Right? That's the problem. Amplitude. Yes.
Second one is additivity.
Yeah. Additivity.
So if additivity is violated, then because this is a whole signal, this impulse response is just one piece of my signal.
Yes.
So in order to get a whole output, I should add them. Then only I will get the whole picture. So, but if that is not the case, additivity is violated, then if I add them, so it is not the output which we want. It is not the exact sum. So that is one thing. Then third one is shift. Shifting means here suppose I am doing this for t equal to 0.
Yes.
And now this is t equal to 1.
Yes.
So if shift is violated, then it may shift by 2 units, it may shift by 3 units.
Very good.
So again we will not get the same result.
Wonderful. You're absolutely correct. Yes. In class, sometimes just for some between undergraduate classes, I think it's a good idea once in a while we get a good response for everybody to give a big hand. Right? So yes. So we do that. Yes. In fact, it's a good idea for two reasons. One is, of course, to encourage. In fact, my students will share the reasons why. Come, you ask Advay. Advay, will you be willing to share the reasons? Overt and covert, yes. So Advay will tell you the overt and covert reasons why clapping hands for good answers is important. Yeah, you can. Yeah.
Yeah, one is to encourage anyone who's talking and giving answers. The other is to encourage other people to also come up and give answers.
Yes, all these are overt reasons, right? Yeah. There's a covert, covert reason Krunal might be able to tell you. Yeah, Krunal can tell the covert reason. No, you don't know. Oh, none of you required a covert. Can you guess the covert? You know the meaning of overt and covert? Overt, yeah, you know the meaning of overt and covert? Yeah, yeah. Covert is hidden. So covert means hidden. And overt, what is obvious, right? What is visible, what is obvious? That's overt.
Covert means to get everybody moving.
Very good. That's a good point. Can you elaborate a little more on that? Yeah. When in the yes, come. Yeah. Covert reason.
I use it a lot in my class.
You do? Very good.
So most of the time when we are continuing our lectures, and some people may drift apart, drift away. So grab their attention back to the class. It's a very good thing to just ask some question or crack a joke or just get them to clap. Yeah.
Very good. That's very correct. That's a good strategy, isn't it? The covert reason, in fact, I tell my students a covert reason is to sometimes wake up some people from sleep. Is that right? There are some people who have gone off to sleep, and this is a very good way of waking people up when they go to sleep, when you ask them to clap for good answers. Anyway, that's on a lighter search. Anyway, so as your name again, Vikash, yeah. Vikas says, each of them when violated causes a problem. When additivity is violated, then if a waveform is actually a sum of many such shifted impulses, now the output would not be a sum of corresponding outputs if additivity does not hold. If homogeneity is violated, these impulses are of different strength, these pulses are of different strength. So you don't know what will happen when there are different strengths, if homogeneity is violated. If shift invariance is violated, by looking at the output of a pulse only at one location, I cannot say enough about what happens at other locations, right. So these are the reasons why all the three properties are required, and you can see that all the three properties are enough. Once you have these three properties, then you can say what the system will do to any input, right. So therefore, an impulse response characterizes the system completely. That means a response to a very narrow pulse like this. Now, of course, there is a more formal way of introducing the impulse and so on, which you will see on your own. But I am giving you, see, I am trying to give you certain important steps which should be taken when you are teaching the subject. Is that right? Very good. So, this is the importance of the impulse response. Very nice. Now, we are going to go to the next topic that we are going to discuss, and that is to understand why we should be using transforms. So, today we will spend some time in understanding what is a transform. Right? And why we should be using transforms. Now, to discuss this further, let us take, all of us are familiar with transforms, right? Which transforms are we familiar with? Can you volunteer and tell me? Yes, loudly, yeah, yes. Laplace transform, Fourier transform, Z transform. Which other? Are you familiar with some other transforms as well? Wavelet transform, yes. Yeah, which? Any? Curvelet, oh, that's very advanced, yes. Ridgelet, well, yeah, it's very advanced. Yes, Hilbert transform, that's correct. Hilbert transform. Any other transform that you're familiar with? Yeah? Discrete cosine transform, that's very correct. Any other? Yes? Z transform, they said, yeah, Z, no? Zach, okay, yeah, all right. Yes? Yes, scale, Karhunen-Liev transform, Karhunen-Liev transform. Yeah, very nice. So many different transforms. Discrete Fourier transform. Is FFT a transform or is it something else? It's an algorithm, it's an efficient algorithm to calculate a transform. Yeah. Any of the transforms that you're familiar with? It's a large number, no? Good enough. There are several more, but it doesn't matter. We're not Mellin transform. How many of you have heard of the Mellin transform? No? Or the Bessel, Fourier-Bessel, or the Hankel transform? No? Heard of? Anyway, doesn't matter. Now, you see, what is a transform? Here again, let us discuss among our groups and volunteer. What is a transform? Now, you have, see, all of you are so familiar, all of you, rattled off so many transforms. What is it that runs across all these transforms? Why do we need to go into a transform domain? Discuss among yourselves and tell me, volunteer. Discuss first among yourselves. Why do we need transforms? What are transforms and why do we need them?
So, transform is the space in which we will be transforming the signal, wherein we can see some different properties inside the signal. And second is we can save the data in some smaller space also. So, that is the second reason we go for transform. And the third can be the processing also will be a small one.
The first thing you said was being able to
see some different properties
different view.
if we transform the signal.
Very good. Different view. The signal. Yes. Okay. Yes.
Second is we can save the signal in smaller space.
More efficient representation. Okay.
And the third is the processing on the transform domain signal will be much easy
Yeah.
in the than the previous.
Very good. Ease of process.
I think I know these skills.
That I think. Yeah, that's very interesting. Now, that's very correct. Yeah, so these are definitely important aspects of a transform. You've come up with so many transforms. You said Fourier transform, Laplace transform, Z transform, wavelet transform, discrete cosine transform, Zach transform, Hilbert transform, right? And some of you also mentioned more advanced ones. Okay. Now, try and think from these different points of view. You're going to when you teach transforms in the class, the first thing that students would want to know from you is why are we going to look at a transform domain? Of course, these are very good reasons, right? Let's now focus our attention on the Fourier transform, right? So we'll take one transform at a time. We'll take the Fourier transform, then we are going to see, in fact, now I told you, when I teach, as I said in the morning, I typically divide the signal systems course into 4 modules, right? What are the 4 modules? The first module, which we discussed almost until the previous class, was systems module 1. Signals and systems in the natural domain. Module 2 is what we are now going to discuss, and that is signals and systems in the Fourier domain. Now, in discussing signals and systems in the natural domain, we forgot one thing. We forgot that the independent variable could be either continuous or discrete, right? And actually, we should have discussed systems of both kinds, where the independent variable was continuous and where the independent variable was discrete. And then, of course, the question comes, is it possible that you have the input with a continuous independent variable and the output with a discrete independent variable, or vice versa? That means, can the basic nature of the independent variable be different at the input and the output, right? So these are questions that we need to worry about. Now, the properties that we discussed, all of them will not even be meaningful if the nature is different at the input and the output. Linearity will be meaningful. Shift invariance will not be meaningful, right? Causality also will not be meaningful. Stability may be meaningful. So, if you have different kinds of input and output independent variables, I mean continuous and discrete, then we have to worry about which properties we talk about, right? So, when we expose the student initially to module 1, it is not very useful to talk about different kinds of input and output variables, right? We either treat both of them as continuous or treat both of them as discrete. Now, now that we have concluded on module 1, I am going to give you a task which you all should think about when you do your peer learning sessions, and which my teaching associates will also coordinate, right? I am going to give you the task now, and you must then, execute this task. With the systems in the natural domain, the peer learning task is this. And peer learning means, see, you will have 8 hours, out of which for each of the modules you should spend 2 hours, where groups will perform a task and they will share, with the whole class what they have done, right? It's like you do your own development and you must share, that all of you carry away something with you, and the teaching associates will help you with that. The peer learning task for group 1 is, in fact, I give you more than one peer learning task for this module 1. The first and T is particularly, you should note this down. Yeah. So the peer learning task is, and all of you should note it down in your notebook. Write down as many examples. So first write down many examples of systems having and not having specific properties. Among the 5. Now I'll explain what I mean. What are the 5 properties we talked about? Additivity, homogeneity, shift invariance, causality, stability. 5 properties, basic ones. So how many possible systems can there be? Each of the properties can be absent or present. So 2 to the power 5, 32 possibilities. Is that right? You must be able to create examples of all the 32. So what you do is you do a jigsaw between yourselves, right? So some of you can come up with examples of some like that, right? So you must now, I'm going to ask you to volunteer. I would like to have, or maybe let us do it this way. All the group leaders will be the volunteers. So all the group leaders will be coordinating this peer learning activity. Is that right? So you must discuss among yourself, because all of you are staying in the hostels, so you can meet even outside and you can work out a way to use these 8 hours with the help of my TAs, right, to carry out these activities. So you must now, what you should do is, you should divide this task between different groups. There are 32 systems to be constructed. 32. And you must construct number of examples of each system, right? So that group leaders should now divide this task out amongst all the different 10 groups. Is that right? So you can do it the way you like. You must learn how to organize a course as well. Who are the group leaders? You raise your hand. Yeah, so all of you must discuss among yourselves, and you must divide this task. That's the first part. Yeah. Well, you can do both. So first, you can, all of them may not have, so you can think of the equation form, but all the equations, it may be difficult for you to think of real life systems. Wherever you can, try and do it. Wherever you can, try and do it. Wherever you can think of a real life system which is modeled by that equation, try and bring it up. Yeah. So, first begin with the mathematical form, but then you can try and think of associated physical systems as well. That's the first part. Second part is, now this is a little more difficult. Construct one system description. One parameterized system description. Which can exhibit all, which can or cannot or does not, which does or does not rather. Each property, I have to explain this. So you have a parameterized system description where you can change the parameters, you can change that part of the system, okay? And by changing the parts of the system, you should be able to make it either obey a property or disobey a property. And this should be possible for all the 5 properties. So in the first part, you are constructing different examples for all the types, 32 types. In the second part of this exercise, you are constructing one system, this one generic system description where you may have by changing the system in small ways, you should be able to exhibit or not exhibit each of the properties. That's more difficult, right? By tweaking the system, it should either obey or disobey. Yeah. System parameter or a part of the description, right? System condition or something. In your description, you change only a part of the description, that there is some variable part in the description which you can change, which can either make it obey the property or disobey the property, right? Now, this should be for all the 5 properties. That's a more difficult part, right? The third thing that you should do in module 1, in the 2 hours that you have for module 1, is you have to give examples of the impulse response. In real systems, in physical systems. So, take a couple of examples of physical systems and identify the impulse response of those physical systems, right. Now, you see, one question that we have not answered is the following. I know that I can characterize a linear shift invariant system by its impulse response. However, this is just existential. That means I gave an argument for saying I could do it, but I have not actually done it. So, I have not said if this is my input, that is the output based on the impulse response. How do I do that? So, we now need to evolve a way of doing it, right. Now, let us understand how we do this. Now I'm going to, I didn't do that here because I want to postpone that discussion a little bit, because although it's really a part of module 1, it is intimately related to module 2 also, the Fourier transform domain. The Fourier transform is going to make our analysis of the system easier for that particular point, right. So, I'm going to take it both in the natural domain and in the transform domain as we go along the Fourier transform. So, now let us first, so now these are the 3 things that you will be doing, and for the 2 hours that you will be having for the module 1, you will be discussing your solutions to these problems between yourself, right. And in fact, you should now also, I would like each group to bring some tutorial problems. So, you are going to construct a tutorial sheet for every module, right. And you must bring problems, and you must make, so all of you must make a consolidated tutorial sheet with different problems, and you must solve as many of those problems as you can during the 2 hours for each module, right. So, you bring several questions, you should construct problems for the class to solve. See, this is also another pedagogical technique. What happens most of the time is the teacher gives questions to solve and the student solves them. This is what is called, you are answering by solving a problem. But there is also a technique called problem posing. Problem posing is also a very important technique. In problem posing, what do? You construct the problem. When you are constructing a problem, the problem must be well formulated. If the problem is not well formulated, you cannot expect a proper solution from the class. So, you must come out with well constructed, well posed problems to be discussed. Now, I have given you some problems to discuss, but you must also come in each of the modules prepared with some problems that you are going to pose to the rest of the class. And they must each group must come out with different problems, which means after you solve these exercises which I have given you, you must also bring new problems that you are going to solve. Each group must bring several problems, because it's possible that you may come and give a problem, and then that problem may, you have constructed the next group has come up with some problem, but that problem may have got exhausted. So, you have to be ready with a new problem. Is that right? So, you have to come prepared with several problems which you are going to pose. Is that right? And each group will be posing a problem to the whole class on each module. Each group will be posing a problem to the whole class on each module. and the whole class will be solving it. Is that clear to everyone? Now, that process itself will take about 1 to 1.5 hours, 1 hour, let us say, because each problem, maybe more also, right? And then the other part should be for solving the problems that I am giving you, right? So, this is how you will arrange your 2 hours for each module. Maybe the time may fall short, but you do as much as you can, right? Okay, very good. Yes. Yeah. Yeah, the peer learning activity will begin day after tomorrow for this course, but it will go on for the next 10 days, almost next 7 days after that, as per the slots that are given for this course, right? Yeah, all right. Now, let us come to the second module. We will come to the second module now. Now, in the second module, we are going to discuss the Fourier transform. Now, the first thing that we want to understand is, what is the Fourier transform? What is our intent in the Fourier transform? Our intent in the Fourier transform is to think of signals in terms of sine waves. Now, you see, to answer why we want to think of signals in terms of sine waves, we need to answer that one question which we have not answered so far, right? That is, I know that the impulse response characterizes the system completely, right? But how can I find the output from the input if I have the impulse response, right? So, let us answer that question first. So, you have a system xt. Let's take the case. In fact, let us begin now. Let's, for variety, let us begin with a discrete system. So, here both the independent variable at the input and the output is discrete, right? It is easier because we first understand with a discrete system and we can generalize to or we can adapt it to a continuous system, right? So, in a discrete system, the time is discrete. So, let us assume that you will make the spacing uniform. So, it means that the separation between successive points in time is the same. So, it is uniformly spaced, the points at which the time occurs. Let us assume the independent variable is time, and let us assume that the spacing of successive points is uniform. Is that right? So, we give a name to the index. Here, instead of a continuous time variable t, we will use a discrete variable, let us call it n. N denotes the instance. So, n equal to 0 means the 0th point, n equal to 1 means point number 1, n equal to minus 1 means the point before 0, because you can have as much extent as you want before 0 and as much extent as you desire after 0. Is that right? So, you have the input x of n, you give it to a discrete system, and you have the output y of n. Now, suppose you have studied this discrete system from the point of view of the experiment that I prescribe. What is it? I give an impulse. Now, what is a discrete impulse? A discrete impulse is very easy to describe. A discrete impulse is often denoted by delta n, and it is 1 when n is 0 and 0 when n is not 0. Simple, right? The first question is, how do you write down any input in terms of discrete impulses? Can I write down xn in terms of discrete impulses? Now, to do that, I need to think of doing 3 things. I need to be able to construct every point on the discrete signal, and I want to do it with just this one impulse. So, what do I need to do? I need to shift this impulse to lie at different places, and each of those shifted versions has to be scaled by a different value, and then all these scaled and shifted ones need to be added. Is that right? Let us take an example. Suppose you have a discrete signal which is like this. It takes the value 5 at 0, it takes the value -7 at 1, it takes the value 4 at 2 and 3 at -3 at -1. Now, how do you think of this as a combination of discrete impulses? You say there is a discrete impulse at 0, 1, 2 and -1. The impulse at 0 is multiplied by 5, the impulse at 1 is multiplied by -7, the impulse at 2 is multiplied by 4, the impulse at -1 is multiplied by 3, and all these are added together. Right? That is what you are saying. So, effectively what are we saying? We are saying this is equal to 3 times delta. Now, you see, if I shift the impulse backward, how does it reflect on the independent variable? N becomes n plus 1, right? Because delta n plus 1 will be equal to 1 when n plus 1 is 0, which means n equal to -1. Is that right? That's right. So, 3 delta n plus 1 plus 5 delta n plus, or rather -7 delta n minus 1 plus 4 delta n minus 2. This is a way of expressing this set of 4 samples. Is that clear to everyone? Yeah? Anybody has a doubt with this? This is very clear, right? So, similarly, you can expand it to the whole of xn. So, you can say xn is equal to summation k going from minus to plus infinity x of k delta n minus k. Okay. Now, based on this, suppose I took this discrete system and gave it an impulse as an input, right? I gave it the impulse as the input. And I studied the output, let us call it h of n, right. Now, this is the impulse response, this is the impulse response. How do I write down the output in terms of the input and the impulse response? It's very simple. I know that delta n produces Hn. So, what will delta of n minus k produce for a fixed k? What will it produce? H of n minus k, that is very correct. What will xk times, and what property are we invoking here? Shift invariance, right? What will xk times delta n minus k produce? Xk times Hn minus k. By the way, how many of you have registered in Moodle? All of you have registered. So, in the course, have you been able to access my course on signals and systems? So, how many of you have been able to access the course on signals? Activity. Okay. Okay. Yeah, so you can go and see, all of you should register. I think once you register once, then all the courses should come, isn't it? Yeah, so my course also will come. I put up my course outline there. There are also several, there is a video list there. So you can make use of the video list, you can even see a couple of the videos. Just see if some of you are able to see, it will be nice. Yeah. And then of course you have summation over k xk delta n minus k, giving you summation k xk Hn minus k. Okay. What property are we, now what are the properties invoked in each of these? This invokes shift invariance. What are we invoking here? In this step, what are we invoking? Which property are we invoking? Homogeneity. Yeah. And what property are we invoking here? Additivity. So, shift invariance, homogeneity and additivity. Is that right? We are invoking each of the 3 properties. Now, this is the input. This is x of n and this is the output, okay. So, you know how to calculate the output in terms of the input when you know the impulse response. This is what is called constructive, the proof is constructive now. You know how to calculate the output given the impulse response and the input. Now, tomorrow we will take further from here, right. When I come to the class tomorrow at 9 o'clock, we will take up further from here. We have done this for the discrete case, now we will do it for the continuous case, right. So, yeah, you are able to access? PDF, yeah, right. No, the PDF file, that is a course outline. So, it has a video list at the end, just see. Yeah, the links are there. So, you can start seeing, you can have a look at the links. Those links will have all the material. So, you can use those. Can you see the video list? There is a video list of YouTube links, right. You can look at it later and, right. Okay. So, I am stopping here today. We will meet at 9 o'clock tomorrow.